So hello everyone, my name is Xiaofan Zhang, a PhD student from the University of Illinois, Urbana-Champaign. So today I would like to share some experience of my research related to the FPGA-based deep neural network design on the power system. So my is implementing long-term recurrent convolutional networks using HLS on the power system. So here, why we need to accelerate LRCN, which is the long-term recurrent convolutional network. LRCN is one of the most effective modules available today, which has a wide range of applications, such as the activity recognition, the image video classification, captioning, storytelling. The most important feature of LRCN is that it combines both CNN and INN, which means it can capture both features from the spatial and the temporal, features. So it's very interesting and very useful. So we need to make this network run fast. So we try to make an accelerator for it. So here, currently we have different choice for inference on the deep neural network. GPU are very popular today. People use GPU for training, for inference, because the high bandwidth, the high throughput, and the very high performance. And of course, GPU take a lot of power consumption. Also, people can use CPU, and thanks to the multi-thread technology and also the higher frequency, GPU can be fast. However, it also takes more than 60 watts. In terms of the dedicated design, we can use the ASIC to accelerate. ASIC is very high performance, and of course, it's very high efficient. However, ASIC suffer from the longer time to market, and also is not flexible. So in terms of the trade-off among the performance, flexibility, as well as the energy efficiency, we can choose FPGA. So here I give a table listing the result of the unexpected inference latency here. And I show the efficiency. So you can see the FPGA-based design actually achieved the highest energy efficiency, peaking at 23.6 image per second per watt. That means it's very suitable when we try to accelerate the neural network in a very small device, such as the edge device. So, however, FPGA also have the problem, which is the memory limitation. Very small amount of memory in the FPGA, no matter the on-chip memory or the off-chip memory. And also, FPGA is hard to program. You need to use the RTL language to program the FPGA. So my solution is that to overcome the memory issue, we use the CABI interface, which is the Coherent Accelerator Process Interface. So by using CABI, the accelerator can share a huge amount of the memory on the CPU side. In the power system, it can be up to 500 gigabytes or more. Also, the accelerator are the full peer to the whole CPU, which means the accelerator can directly access the memory which belong to the CPU side. So the other problem is the time-consuming and challenging RTL programming. Also, there is the hardware verification, the resource allocation, because we only have a very limited resource in the FPGA. So how to make this work easier? We use the HLS, which is the high-level synthesis. It's a design flow provided by Xilinx. Here you can use a high-level language, such as the C and C++ for upshot description of the hardware components. And also, it's easier to debug, and it's easier to do the design space exploration, because you can take advantage of the built-in pragma, like unrolling, like partition. And so let me talk about the challenge when we try to design this accelerator. LRCN is very complicated. Here I list two figures. If we try to use a K80, it will take 124 milliseconds. And if you try to use an Geno E5 CPU, it will take 190 milliseconds for process single image. So in terms of FPGA, which is very limited by the resource, we need to come up with a very precise optimization scheme, such as how many resources should be allocated into the first layer, how many resources should be allocated to the other layers. And also, we need to face the memory issue, is the memory access latency here, because the on-chip memory is not enough for accommodate all the parameters. We need to use the external. So we need to come up with some hierarchical memory design to hide the memory access latency here. So here is a diagram of the LRCN. The front part is the CNN, which is an ArnexNet in most cases, and the back end is RNN. Here I list the LSTM, which is a common use here. The image is input from the left side to the right side, and the CNN, all the features are captured by the CNN. The feature will be passed to the LSTM to generate a proper description, such as a test message. And the table here shows the different characteristics of different layers. In the convolutional layer, most of the it will spend a lot of computational resource, which means the convolutional layer will be it's not memory bound, it's actually computational bound. So in the fully connected layer is quite different. It's actually a memory bound. You can see it's 67% of the resource are allocated to the memory. So right here, right in the last is the RNN, quite in the middle of the convolutional and fully connected layer. So with different characteristics, we need to have different scheme to accelerate this network. So here is, we propose a resource allocation scheme called WAM to generate the guideline for resource allocation. So WAM will analyze the computational demand of each layer and generate a theoretical design, such as how many DSP you should use for a certain layer. So the idea is to find a lower bound of the latency. So in the equation 3, we use a Conkey inequality to find the lower bound. And we can achieve this lower bound unless we reach a certain condition. So the condition here are highlighted in red, which means in the layer I and J here. Let's see. Oh, it's here, right in the middle. The right highlighted in red here. It means the convolution is that the resource allocated to layer I and J should follow the ratio between the square root of the computational demand I and the computational demand J. So follow this guideline, we can decide the resource allocation scheme. So the other issue is LRCN contains a large amount of loop iteration. The efficient implementation of loop will directly improve the overall performance. So here we propose an HLSIP, which is showing in the figure 8. It can be unrolled in 2 dimensions, the CI dimension, which is the input channel, and the CO, which is the output channel. So in this HLSIP, it contains the multiplier and the tree adder. Is very compact design here. And use this IP, we can build a whole convolutional network, which is showing in the figure B. So this convolutional layer is tail across the input channel and the output channel. And each small tail is handled by one HLSIP, which is showing in figure 8. So we can assemble the output and to generate the whole output of these layers. So also we try the different optimization schemes, such as pruning and the quantization. We cut the network, and at the end, the network is reduced from 2.22 GOPS to the 1.45 GOPS. So it's 1.5 times reduced. And we also have different quantization scheme. We try to use 16-bit and 12-bit for the feature map and the parameters, respectively. And also we use Caffe to retrain the whole model to make sure suffer accurate up. And as I mentioned before, the memory issue is pretty significant. So we try to design a hierarchy memory. So the first step is to turn the multi-dimensional weight into a linear sequences. So here on the left side, the multi-dimensional weight is turning into linear sequence here. And we also insert a FIFO and a ping-pong buffer between the memory and the computational engine. So the FIFO is what for prefetching a small amount of data. And also here, ping-pong buffer is what for hide the memory access latency. So in this design, we can use the external memory, but we will not introduce the additional latencies. Also, if we try to use 12-bit parameter, there's the other issue, which means 8-bit here are not going to use because we are using 512-bit bus interface. So to make the to solve this problem, we actually cut the data into 3 pieces, and we try to access the same data in 3 times, and at the end we assemble the data. And so in this case, we can fully use the memory bandwidth, and there's no waste here. So here I'm going to talk about the full system design. So in the CABI integrated design, we also have different challenges here. The first challenge is related to the Xcin interface, because we are trying to use the HLS design flow, and HLS will generate an Xcin interface, which is worth for communicate with the whole CPU and your accelerator. Also, we need to remove the Xcin bus because we already have the CABI interface. When we remove the Xcin bus, there's some other issue, which means we need to communicate with the whole CPU. So we need to design our communication scheme. And if you try to map the large design such as the LSN, we may need to manually do the place and route because we are facing very tight timing constraint. And also, the CABI interface will reserve a small amount of resource in the FPGA, which we may need to have if we try to use that portion of the resource. So the first solution to remove the Xcin interface, what we are trying to do is we need to prepare a huge chunk of memory, and we need to specify which offset is related layer. So it actually requires a little bit more effort when you try to program your accelerator, because you need to figure out what's the offset of a certain layer. But the good thing in removing the Xcin bus actually help us to reduce the resource utilization. Here we try the same design, and the left side is using the Xcin interface, and the right side is using the CABI interface. So we can see there is 6% job of the LUT and 3% of the flip-flop. And because we are using, we try to build a small BRAM as a buffer, so we actually use more BRAM in this case. But in the end, we can save the LUT and flip-flop. So since we are trying to decide the communication scheme, we need to take advantage of the CABI interface. So CABI has 2 port scenes. Hello? Yeah, it's working. It's working, okay. Yeah, it provides 5 different lower layer components on top of the PCIe physical channel, but we are not directly using these 5 modules. Actually, on top of them, we have 3 more abstraction layer, which is the control, DMA, and the MAIO. We use the control layer or the control module to transfer the control signal, and the DMA to transfer the data between the host CPU and the accelerator. So on top of this layer is our customized accelerator. So here is the detailed finite state machine design. And the major finite state machine is on the bottom, which has 5 different stages. So the key component here is the copy and processing stage. When we step into the copy stage, actually the data is copied from the memory to the local VRAM here in the FPGA. And then the finite state machine will jump to the processing stage and give the signal to the LRCN IP, and the LRCN IP will start working and consume the data here. And after it generates the result, it will jump to the right stage, which means we will get the data from the LRCN IP. And in usual, the copy, and there are several iterations here because one copy only copy a small portion of data from the memory to the local VRAM. It may take several hundreds of iterations until all the data is copied to the VRAM, and then is processed by the LRCN IP. And the smaller finite state machine is worth for coordinate the input from the local VRAM and separate them from 1024-bit to 512-bit, and then send to the LRCN IP. So here we have several steps of the memory transformation here. And we intend to hide the latency because we have several buffers here. So in our experiment, this design actually helped us to hide the memory access latency. So in the future, this might be improved, but here we stick to this current result. And in summary, we have a 6 steps to generate our design. The first step is to use the very popular machine learning frameworks such as Caffe or TensorFlow to design your module, to train your module. And we start from step 2, and network pruning, which means we can cut the network because they are very redundant here. So we can use less parameters and less layers, and we can still get the same accuracy. So we also try the quantization in this step. So in the next step, we will use our RAM, which is the resource allocation scheme, to generate the different allocation scheme for different layers. So following this step, we can start writing our HS code, which is basically the C code. And then we can go through the HLS and get the RTL design. And once we get the RTL design, we can stitch this accelerator with the CABI framework so we can launch our design on the power system. So to demonstrate our design, we have 3 different strategies, which is the baseline, which is very basic LRCN. We only generate one LRCN IP and try to run this IP in the FPGA. And the batch scheme, which is we use 2 identical LRCN IP on the same FPGA. We try to use batch to simultaneously run 2 images and generate 2 sentences. And we have semi-batch. In this case, we only generate 1 CNN, which is the front end of LRCN, and we have 2 RNN. So in this case, 2 images will be processed by the same CNN in serial, and all the features of these 2 images will be passed to the RNN at the same time. So here is the baseline version. We have 4 different schemes. We try to increase the resource utilization. We try to see what's the best performance you can get in this particular FPGA. So when we try to allocate near 16% of the resource, we can reach the highest performance. And in this case, it's 17 frames per second. So in the batch mode, we have 2 smaller LRCN IP. We share the weight we share the control signal, but we have a different data path. So in this case, each LRCN can reach 10 frames per second. So we have two. So the final result is 20 frames per second. And in the semi-batch, we have a serial portion here. The CNN will run twice, and then all the feature will be passed to the IronNet. So the result is 15.4 frames per second. So in summary, we also compare to the CPU and GPU design. These two designs are using batch one skin, which means only one image coming from outside and generate one sentence. And the orange dot here is, the four orange dots here are the baseline, and the white dot here is the semi-batch, while the yellow dot here represent the batch design. So we compare the batch and the ideal batch 2 design of the GPU. We can see there is a huge improvement in terms of the efficiency here. Is the normalized throughput per watt. So we also compared the skin 4, which is the batch 1 version of the GPU's batch 1 version here. We have some interesting results. So in terms of the efficiency, the FPGA-based design actually get 26.6x. And if we are trying to compare with the performance here, the normalized throughput here, we can get 2.1x. So it demonstrates the CPU-based design can have a better power efficiency, and of course, in some cases, it can get better result in throughput. So here, I try to conclude our work here is we try to implement an FPGA-based accelerator in the power system using CABI interface to help us to get rid of the memory limitation. And we try to design our own finite state machine because we don't have the X-in interface. We don't have any Xilinx generate IP. And we try to adapt the actual S design to the CABI environment. In this case, we don't need to write the RTL program, so it saves a lot of time to using HOS. And in the end, we tried different strategy. We have 3 different strategies, the batch, the semi-batch, and the basic version. And we generate a better result than the CPU and the GPU solution. So that's it for my talk, and thank you for your attention. So, please.
So why did you, is the focus of this to reduce power? Is that what is going on?
Excuse me?
Is the focus of this exercise to reduce power consumption?
Is this to try to reduce the power consumption using CABI? Actually, using FPGA can save you power because FPGA have higher power efficiency, and FPGA have some other issue, and power can solve one of them, which is the memory limitation. FPGA, the onboard memory on a high-end FPGA is very small. It's like 10 megabytes. So you can't fit a large neural network on chip, on the FPGA chip. So you need to use the external memory. And right now, FPGA, most of the FPGA, I see Vertex, the Xilinx Vertex 7 serial, we use DDR3 FPGA. So you will get 4 gig of 8 gigabyte, very slow memory. And here, if you are using CABI, you can get 500 gigabyte memory on the CPU side. So it solves you the limitation of the memory. When you try to map a huge neural network, 8 gig may not enough. So we are using FPGA for small, for the reduced power efficiency, reduced power, and we use CABI to solve some existing limitation in the FPGA. So in this case, is the memory issue. Okay.
So this is for inference.
Yes, here. Is our design for inference? Yes. And the training part happen in the GPU. And we try to do different inference in FPGA because I think it's not mutual, it's not good for people right now to do the inference in FPGA because you can't have support library, you don't have the support programming, like the SDK, the library. So all the thing you need to do is write from scratch. So no one are willing to do that. So that's the one drawback of using FPGA for training. But after finish all this problem, you have a tool chain to help people to use FPGA for training. I think more people will be willing to using FPGA.
Yeah, but in training, you don't care about power. You don't care about power, you care about cost.
Yes.
And the cost FPGA just is.
Yeah, but training can happen in the cloud side, right? You can use cloud for training. But when you talk about inference, it's more diverse. You can use edge device, you can use cloud device. When you talk about some IoT device, you care about power. So in that case, FPGA can help. Okay. Oh, please. You mean DSP? Okay. Actually, we don't involve DSP here. Let's see here. And we try to use actually the DSP are using inside the FPGA. You know the most critical resource in FPGA actually is the DSP unit. Yes, we need to do the multiplication.
Yeah, so DSP might be a very good candidate for this. Because, yeah, after all, your math is being done on DSP.
Yes, that's true. Yeah, but since I ran through a lot of paper, and actually DSP is not that popular in machine learning community. Yeah. Yeah, I try to figure out. I think FPGA kind of involved the DSP. Yeah. Please.
How much of the system memory have your model used?
Okay. My model, the LRCN, used more than 300 and let's see, less than 400 megabyte. So between 3 mega. So it's just for one module. So here is like a test case. You use one LRCN, but what if you try to use different module and stuck into the same FPGA? You try to use 4 or 8, and that we need to use more than 1 gigabyte memory and 2 gigabyte memory.
So that was my concern, because when you compare your performance with GPU, you run the same model with the same batch size, which consumes like half data, and that's really bad for the GPU. You try to
Yes.
utilize the whole memory of the GPU by running a larger batch.
Yes, that's true. The GPU here actually using different data format, but we stick to the same batch size.
Yeah, so you are utilizing the full power of the GPU.
So here we compare mostly, we compare the latency, not the throughput. So throughput is not good for FPGA because you don't have a high bandwidth memory first. You don't have a large number of the computation kernel inside. But the latency can help when we're using the GPU, when we're using the FPGA, I mean. So in this table, we use the same batch size. Here, CPU and GPU is using batch 1. So of course, GPU can use more. GPU can use batch 100 or 1,000. It depends on how many memory you use. But to be a fair compare, we use both of them using the batch 1. Okay. No, actually, but the board we use is the Alpha Data 7B3. The Alpha Data board. We plug the Alpha Data board into the Power 8 machine. So because Alpha Data already provided CABI interface, and the Power 8 there's a CABI interface embedded, so we can use them. So we don't design our own board. We just use this FPGA on top of the power alpha data board. So we program the FPGA and using the internal interface to communicate.
How easy was it to use HLS?
If you can write C code, you can use HLS. And basically, HLS is a subset of the C code. It's simpler, straightforward C code, but you need to think about how, what's the programming strategy will look like in the hardware. So you may need to pay attention to several memory access issues because you are actually programming the hardware. So it's not straightforward in the software, but it's not difficult. I think spend 1 month is more than enough for a software developer to learn how to program in the hardware. And of course, if you try to design a very high efficient module, you may need to spend more time. So, but it's very easy to pick up. Okay. Okay, thank you.